Well, hey there, everyone. Today we're going to get started on L'Hopital's rule, which is another tool that we can use to evaluate limits if the limits are of a particular variety. So let's take a look at what we're talking about over here. Okay, so Indiana Jones's adventures lead the archaeologist to a 1935 Shanghai casino where he attempts to trade the ashes of Nurhaci, the first emperor of the Manchu dynasty, for the peacock eye diamond that was once owned by Alexander the Great. While in the casino, Dr. Jones most likely played a round of no-limit poker, which gives us an excuse to talk about limits again. Okay, so that's kind of lame. I understand. Limits. Sure. Okay, suppose that for the functions f and g, if we evaluate them both at some point a, we get 0. So if this is true, then if you take the limit as x approaches a of f over g, you get basically a meaningless expression, which is 0 over 0, or you may want to think about it as 0 over 0. And that 0 over 0 is what we call an indeterminate form. Okay, so in order to help us with an indeterminate form, a limit that has an indeterminate form, we have L'Hopital's rule, which was named after L'Hopital's rule, which was named after Guillaume de L'Hopital, French mathematician in the 17th century. So this says, suppose we have a 0 over 0 indeterminate form, or we have some kind of infinity over infinity, which is just as meaningless as 0 over 0. Well, if that's true, then instead of evaluating f over g, we could evaluate f prime over g prime. So we can use derivatives to help us figure out our limits, which is a nice way that calculus and limits kind of dovetail together yet again. So we're going to get an example of this with the limit as x approaches 0 of 1 plus root x minus 1 over x. The first thing we need to do is to verify that this is actually an indeterminate form. So when x goes to 0, this becomes root 1 plus 0 minus 1, which is 1 minus 1, or 0. Clearly, the limit as x approaches 0 of just x is just 0. So when I evaluate this limit, I'm going to get something that's like 0 over 0. And that means that this is an indeterminate form. So this is an indeterminate form. We can now use L'Hopital's rule. So it's very simple. We just take the derivative of the numerator. So the derivative of root 1 plus x, that's 1 over 2 root 1 plus x. And then the derivative of x is just 1. If we simplify that, we get we get the limit as x approaches 0 of 1 over 2 root 1 plus x. And when I substitute 0 now, I get 1 over 2 root 1 plus 0. So this limit is actually just 1/2. Not a problem. The derivative made that limit so much easier. So let's take a look at a more advanced form. And this is if we get a 0 multiplied by infinity, or infinity minus infinity. Okay. Both of these are indeterminate form because they are kind of meaningless. I mean, 0 multiplied by infinity, kind of who wins here, the 0 or the infinity? I don't know, because infinity isn't really a number. It's kind of a concept, I guess. Same thing with infinity and minus infinity. Which infinity is going to win out? We don't know. So to illustrate what to do, we've got x, the limit as x approaches infinity of x sine 1 over x. And when we evaluate this, if x goes to infinity, this is going to be infinity multiplied by the sine of 1 over a number that goes to infinity. and that's equivalent to sine of 0. And sine of 0 is 0. So that's the infinity multiplied by 0 thing. We're going to use properties of limits to, well, not even just properties of limits. We're just going to use properties to turn this into something which is indeterminate. So here's what we're going to do. We're going to take this sine of 1 over x, and we're going to put it on our numerator. And we're going to take x, and we're going to put it in the denominator with the penalty of making it the derivative, or the reciprocal. So this becomes sine of 1 over x over 1 over x. And when we do that, we create something that's a true indeterminate form. So let's take a look at this. We've got x sine 1 over x, limit of, and then this becomes sine of 1 over x divided by 1 over x. That's just algebra. X times a times b is the same thing as a multiplied by 1 over b. We're going to use L'Hopital's rule next. So the derivative of sine is cosine. And then the derivative of 1 over x is negative 1 over x squared. The denominator, the derivative of 1 over x, is negative 1 over x squared. Okay, so you take the derivative of the numerator and denominator separately. What happens here is that this factor and this factor both cancel out, giving me just the cosine of 1 over x over 1. And now we can evaluate. As x goes to infinity, 1 over x goes to 0. So in my head, what I'm doing is we're doing the cosine of the limit as x approaches infinity of 1 over x. That's equal to the cosine of 0, and the cosine of 0 is just 1. So if you take a look back at where we started, this equals 1. L'Hopital's rule. And then this is another type. We've got 1 over natural log of x, 1 over x minus 1. This time x is going to approach 1. Now the natural log of 1 is 0, so this is 1 over 0. And 1 over x minus 1, that's also going to be 1 over 0. And maybe we don't know it, but 1 over 0 basically goes to infinity. So what you're looking in essence at is infinity minus infinity, which is one of those disguised indeterminate forms. What you're going to do is put everything to a common denominator. So with a common denominator, we're going to multiply the first fraction by x minus 1 over x minus 1, and we multiply the second fraction by the natural log of x over the natural log of x, and what we get is x minus 1 minus the natural log of x over x minus 1 multiplied by the natural log of x. Now the thing that I didn't say is we've got to verify that this is an indeterminate form. So let's substitute 1. If I substitute 1, this goes to 0, this goes to 0, this goes to 0, and this goes to 0. And of course 0 times 0 is 0, so this form is 0 over 0. Indeterminate form, and that's what we want. We want the classic 0 over 0 indeterminate form. So since this is an indeterminate form, we're going to use L'Hopital's rule. Over here, I always like to write L'Hopital, just so that I know what's going on. I know it's written over here, but as you do your work, just write L'Hopital over here, so that we know what happens. The derivative of x minus 1 is 1, minus the derivative of natural log of x is 1 over x. And then this is going to be a product rule here. You've got 1, which is the derivative of x minus 1, multiplied by natural log of x, plus x minus 1 multiplied by the derivative of natural log of x, which is 1 over x. Product rule on the denominator. All right, product rule on the denominator, we're going to simplify both sides by multiplying by x over x. So we're multiplying the numerator by x. We're multiplying the denominator by x. So this gives me x minus 1. And on the denominator, that gives me x natural log of x plus x minus 1. Okay, let's check. Is this still indeterminate or not? If I substitute 1, the numerator gives me 0. The denominator gives me 1 multiplied by 0, which is 0, plus 1 minus 1 is 0. So I still get 0 over 0, which says that if I want to evaluate this indeterminate form, I can take the derivative again, which just goes to show you that you can kind of chain together a whole bunch of L'Hopital's rule until you get to something which you can evaluate. But you have to make sure that you have an indeterminate form. So let's take the derivative of the numerator. You get 1. The derivative of the denominator, well, this first term right here, we need to use a product rule. So the derivative of x is 1 multiplied by natural log of x plus x multiplied by the derivative of natural log x, which is 1 over x, which is, and then plus 1. Simplify that. That is 1 over natural log x plus, and this is going to be 1 times 1, so plus 2. Now notice that this is no longer indeterminate. So when I take the limit as x approaches 1, I can just directly substitute into this now. And as x goes to 1, this goes to 0. Everything else is a 1 and a 2, and that gives me 1/2. This limit is 1/2. In other words, this infinity here is a little bigger than this infinity over here, which is weird. Okay, we're now talking about infinities where one is bigger than the other. Okay, so let's move on from there. Here are the important ideas. We've got the indeterminate form, which you have to be able to recognize. And for indeterminate forms, you're supposed to use L'Hopital's rule, which basically means take the derivative of the numerator and then take the derivative of the denominator and evaluate the new limit. So with L'Hopital's rule, I do have these hints for you, or these tips. Number 1, simplify. Make sure you simplify. Always check for indeterminate form. More than one student has been burned because they used L'Hopital's rule on something that is not indeterminate. Gotta tell you. And then the other tip is you can use L'Hopital's rule multiple times. So if you take L'Hopital's rule and you still get something indeterminate, take L'Hopital's rule again. It's okay. Let's check our understanding. Use L'Hopital's rule to evaluate. So first of all, we need to make sure that this is indeterminate. So let's substitute pi over 2. Sine of pi over 2 is 1. So the numerator is 1 minus 1. Denominator, cosine of pi over 2. Well, no, that says cosine of 2 times pi over 2, which is cosine of pi, which is negative 1. Negative 1 plus 1, yeah, that's 0 over 0. So it's time for us to use L'Hopital's rule. So let's use L'Hopital's rule. What is the derivative of sine x? And I think I heard you all say cosine x. What's the derivative of cosine? It's negative sine. But it's negative sine of 2x, so we have to take the derivative of 2x as well. That gives us cosine x over negative 2 sine 2x. Let's check if this is indeterminate now. If I substitute pi over 2, I get the cosine of pi over 2 over negative 2 multiplied by the sine. 2 times pi over 2 is pi. And what do we got? We got 0 on top of sine of pi is also 0. Hey, look at that, folks. This is still indeterminate. So we have to use L'Hopital's rule another time. All right, let's use L'Hopital's rule again. We're going to find the limit as x approaches pi over 2. Now the derivative of cosine is negative sine x. The derivative of negative sine is cosine. And then we have the 2x. So this is going to become negative 4 cosine 2x. Let's try substituting. If I substitute pi over 2, sine of pi over 2 is on the numerator, and the denominator is 4 multiplied by the cosine of pi. Sine of pi over 2 is 1. Cosine of pi is negative 1, so that's negative 4. So that gives me negative 1/4 as the limit. Over here I'm going to write the limit as x approaches pi over 2. Sine x minus 1 over cosine of 2x plus 1. That's equal to negative 1/4. Next, check your understanding problem. X tangent 1 over x. Let's see if what happens if I try to substitute, quote substitute. We're going to get infinity for the x, and then the tangent of 0. Tangent of 0 is 0, so this is infinity multiplied by 0, which we don't like. That is one of the disguised indeterminate forms. So we're going to use a little bit of algebra to turn this into a classic indeterminate form. Limit as x approaches infinity, tangent 1 over x over 1 over x. So now when I do this, I get 0 over 0. So we use L'Hopital's rule. The derivative of tangent is secant squared 1 over x. The derivative of 1 over x is negative 1 over x squared. And the derivative of 1 over x on the denominator is also negative 1 over x squared. You will see those cancel. And then this is equivalent to the limit as x approaches infinity of secant squared 1 over x. Now as x goes to infinity, 1 over x will go to 0. So this is equivalent to secant squared of 0. Secant squared of 0 is, of course, 1. So that takes care of the second problem. Our third problem over here, we've got the limit as x approaches infinity of natural log minus natural log. And if we do that, as x goes to infinity, this becomes infinity over infinity. So we're going to have to do something here about this one. And the idea here, if you look at the hint, is you can actually combine these two natural logs, which I always recommend you do. So this is the natural log of x over 3x minus 3. Now, now that you've done that, this is equal to, and I think you guys saw me do this the other day, the natural log of the limit as x approaches infinity of x over 3x minus 3. Well, how are you going to evaluate this limit, x over 3x minus 3? We already saw one way. We could divide every term by x. So let's do option 1. We could do, this is the natural log of the limit as x approaches infinity of 1 over 3 minus 1 over x, and that just turns into the natural log of 1/3. No problem, you can totally do that. Or option 2, you could use L'Hopital's rule, because this is infinity over infinity. So option 2, natural log of the limit as x approaches infinity. Now the derivative of x is 1, and the derivative of 3x minus 3 is 3. And now there's no x's to evaluate, and this is just simply equal to the natural log of 1/3. So either way you do it is fine. I think you might be better off not using L'Hopital's rule personally, because I think there's less of a chance of making an error if you don't use L'Hopital's rule in this one case. So that's it for today, everyone. Hopefully you have something learned here. L'Hopital's rule definitely makes your life a lot easier with limits. So get really well acquainted with it and use it when you need to. See you next time.